Welcome to NET320. This is the right AWS network architecture for the right reasons. I'm Justin Davies. I'm a solutions architect based out of San Diego, California. My partner in crime, Bhavin Desai. He's based out of Seattle, with the rest of Amazon for what it seems like. So today, we're probably going to use like every second that we have. We've got a ton to cover. And I did want to make a call out because there was a lot of announcements with regards to networking today. Nothing on these slides are affected by that. So we're going to talk about VPN. We're going to talk about Direct Connect. We're going to talk about a lot of different things. It's all still relevant as far as the architecture goes. This is a 300-level talk. So we're going to go over a mixture of pretty deep technical concepts as well as some higher-level things that we want you to make sure that you understand. Throughout the slide deck, you're going to see these little picture icons pop up. Sometimes they'll spin around, sometimes not. We put them at the end of animations. So like, if a slide's going to have multiple animations, you're going to know if you want to take a picture, if that's your thing, it'll pop up there. We also put them at the end of what we call, or when what we call the 4 tenets of success show up. And that's like this. And so what these are kind of like, if you're going to leave here with 4 things to remember, or 4 takeaways, this is kind of what we want you to remember. This could be best practices, considerations, questions to ask yourself, stuff like that. All right, so to start off, I'd asked Bhavin to basically run us through what a typical AWS customer's evolution in the cloud might look like.
Cool. So to start off with this story, I have a single VPC with 3 availability zones. And I created this VPC because I decided to launch my first ever application in AWS. Now, this was my first application. It's a simple 3-tier web application where I launched multiple public and private subnets. I've got an application load balancer as a front end in the public subnet. And I've got my application logic, or the business logic, in a private subnet, and a separate private subnet for my backend database. Now, this is just a logical representation of my architecture, but in reality, it spans across the 3 AZs, or availability zones. Now, after running my first application in AWS, everything was going smooth. So I decided, why not spin up second application in AWS? And what I did is I carved out a separate subnet inside the same VPC for my second application. Now, this is, after all, what everyone does, right? Since VPC is your virtual data center in AWS. So now my applications were moving into production, and I wanted some sort of observability. So I decided to build up shared services like the custom logging and Lambda-based monitoring so that I get more visibility into my traffic and application. And what I did is I created another subnet for it, and now you can see my VPC is starting to grow bigger. Now my developers started pushing us to support containers workload, and we wanted a strategy where we could run the container workload in our own data center as well as in AWS. So we decided to choose Kubernetes as the platform, and in AWS, we decided to spin up Amazon EKS and dedicating a EKS cluster ENI subnet, and then creating a larger EKS worker node subnet, because at that point of time, I had no idea how many IPs were going to be consumed by the pods that are running on those worker nodes. So what I did is I created an additional secondary CIDR for the same VPC and allocated subnets out of that CIDR just for my EKS workload. So now came a shadow team who decided that they will deploy their own application, but in their own VPC, in their own account, which is dedicated to their business unit. But they still had dependencies with the shared services like monitoring and logging in the main VPC, as well as dependencies with the database residing in the main VPC. Now, to give them layer 3 network connectivity, I decided to spin up VPC peering connection for them. Another team from a different business unit popped up, and they saw the success of first 2 teams, and they were like, yes, we'll spin up our own VPC and launch our own application. Now, this time, they only had dependency with the database in the main VPC, So we created another VPC peering connection. And for logging and monitoring purposes, they decided to use AWS PrivateLink to securely access Amazon CloudWatch and CloudTrail services. This was pretty cool. So now we started seeing a trend where VPC started popping up everywhere. So I decided, let's migrate to Transit Gateway to aggregate this connectivity in a more centralized fashion, because that's easier to manage and operate. Now, I was able to do this gracefully because I kept both systems active at the same time and started migrating fewer routes at a time. So now nobody asked me, but we just acquired another company. This was pretty awesome. But the problem for a networking guy was that it was a completely overlapping IP schema. Well, then I just thought that my SA from AWS was pestering me about PrivateLink since over a year. And then it turns out that PrivateLink is designed exactly for such a situation. So I put the front-end API of acquisitions VPC behind a network load balancer. And from the main VPC, I used PrivateLink to consume those services. Now, this also solved my overlapping IP addressing schema problem. Now, the acquisition was going well, so I decided it's time to expose some more client-server-based applications like my database in the main VPC for my acquisition resources. So I created a PrivateLink, but this time in the reverse direction. Now, this gave a truly integrated service or community between the two services in two different directions. Now, we started getting super popular in the financial sectors. So some of our banking customers had a requirement for us to achieve regional redundancies. So we launched a cookie cutter stamp of our architecture in another AWS region. And we still required the replication between the two regions for our databases to be in sync. So we enabled inter-region VPC peering. And all our front-end connections or transactions were regionally isolated and were local. So up to this point, this was more of our AWS setup. But I forgot to mention that we still had fairly large resources in our on-premises, and there were hybrid workloads which had dependencies. So at first, we had direct connect private virtual interface that went directly to our VPCs. We did not have great way of doing site redundancy at that point because private virtual interfaces do not cross the regional boundaries. So at that point, for getting access to 6 VPC, we needed 6 BGP sessions and 12 if we wanted device redundancy. We quickly ended up migrating to Direct Connect Gateway because it allowed us to connect VPCs around the world from any Direct Connect locations as long as the VPCs have non-overlapping IP schema. So this really helped us to reduce our BGP session from 12 to 2. That was a significant change for us. Now, since the VPCs were already connected to Transit Gateway, we decided to consolidate it further. So instead of attaching 6 VPCs, we set up a new Direct Connect Gateway and attached it to both regional transit gateways. Now, the transit gateway requires a different kind of a virtual interface called as transit virtual interface. And this, at that point, we thought is the simplest way to migrate. Instead of using the same Direct Connect Gateway, we created a new Direct Connect Gateway. Now, as you can see, our primary workload has the north-south connectivity, but we still had to solve the overlapping IP space issue with the acquisitions VPC. We decided to take a look at PrivateLink again. Now, a Direct Connect Gateway can either be attached to 10 VPCs across regions or to 3 transit gateways across regions, but you cannot mix and match both of them on a single Direct Connect Gateway. Also, your Direct Connect Gateway can only be attached to VPCs who have non-overlapping IP space. You cannot even attach the acquisition VPC to Transit Gateway because the Transit Gateway's routing domain, where the Direct Connect is attached, would not be able to differentiate between the overlapping prefixes. So in simple words, it's basically your Direct Connect would have no idea where to route towards for the 10.128 VPC. So to get around this, we set up something called as a proxy VPC or mediator VPC. People call it all different names. But that VPC is nothing but a VPC which has a unique IP space, a non-overlapping IP space, and we installed private links that could expose my acquisitions resources to my on-premises. So this way, now we can attach our acquisitions VPC to our on-premises data center through Mediator VPC and PrivateLink's ability to provide large-scale network address translation. Now, in this model, we can either directly connect to the same transit gateway, or we can set up another direct connect gateway to attach it directly.
So those who never change their minds never change anything. So Bhavin and I both love this quote because it's what some of our most highly scaled and most experienced customers live by. So if I could boil the theme of what Bhavin just went over down to a single thread, it would be one's ability to thrive on being able to adapt and evolve with your customer needs and the lessons learned as you're deploying your services. So what do we have in store today? We're going to do a quick refresher on some of the foundational concepts of the well-architected framework. Then we're going to go through a couple of different typical use case and design patterns. And then we're going to close things out with some tips and advice on how you can all be solutions architects for your own organizations. So the well-architected framework was developed after years of working with our customers in the cloud and learning how to build the most highly scaled, high-performing, resilient, and efficient architectures. Now, the framework itself, if you're not familiar, consists of 5 pillars, which we believe are the foundation for every single architecture. So I'm going to take a second here, and I'm going to define each of these for you. So the first pillar is operational excellence. Now, this is the ability to run and monitor systems to deliver business value, which is a theme here you'll see, and to continually improve supporting processes and procedures. The second is security, which is the ability to protect information, systems, and assets while delivering business value through risk assessment and mitigation strategies. The third, reliability, is the ability of a system to recover from infrastructure or service disruptions, dynamically acquire resources to meet demand, and mitigate disruptions, such as misconfigurations or transient network issues. Then you have performance efficiency. This is the ability to use these resources efficiently to meet your system requirements and to maintain that efficiencies as the demand changes and technologies evolve. And last but not least is cost optimization. This is the ability to run systems to deliver business value at the lowest price point. Now, when you're going through these architectures and you're designing these architectures, you're going to have trade-offs based on your business objectives. And these business objectives usually drive your engineering priorities. So for example, for dev workloads, you might optimize for cost efficiency at the expense of reliability. Or you might do the complete opposite and optimize for reliability at the expense of performance or cost. Okay, so the first one we're going to start out with is kind of the very plain and simple one that, well, at least at face value, it appears simple, that everyone kind of starts out with, and that's the flat network architecture, a single account and single VPC. So this is how VPC was born. You chose a CIDR for your VPC, and you divided it up into subnets in the individual availability zones. And the subnets were basically placed into routing tables where you segmented like traffic profiles or like use cases. So like this is, for example, public and private subnets, if you're familiar with that term. Then we added the ability to add additional CIDR blocks to a VPC. So with a single VPC, you could have up to 5 CIDR blocks. Each of those CIDR blocks can be as large as a /16. Okay? So being able to resize a VPC for some of these customers that wanted to maintain a single flat VPC was really a game changer. Originally, you couldn't do that. Now, I work with several hyperscale customers who do operate hundreds of thousands of services, some microservices, some monoliths, within a single account and a single VPC. You know, it's super simple. There's minimal data transfer to consider, unless you have dependencies where you're crossing AZ boundaries, and ideally that's kind of not what you want to do. And you can have more than 300,000 IP addresses, so it can scale to launch your workloads. Additionally, if you are very diligent about it, you can get proper segmentation with native constructs such as subnets, route tables, network ACLs, even security groups. And then there's other customers that have gone the additional route, doing their own overlays or doing a service mesh architecture with Envoy and App Mesh and stuff like that. Now, the bigger your VPC grows, the bigger your blast radius. And most AWS limits are scoped at either the AWS VPC, the account, or the region. So if you are operating a single VPC that's multi-tenanted, you need to make sure that one of those tenants aren't eating up all the resources and not communicating to the other users, right? How many of you in the room have heard the term "I am ninja"? You know, like, ninjas are super hard to hire, right? And so, like, if you're thinking about cost allocation or policy control and implementation, and you have everyone in the same bucket, it can get rather difficult. So big, multifaceted organizations need to get super creative if they're following this model. So last year, we launched the AWS Resource Access Manager, RAM. And this is a service that enables you to share your resources with other accounts in your organization. And this is things like the transit gateway, Route 53 resolver rules, and even subnets within your VPC. And so I mentioned you can share the subnets in the VPC. And so in this model, you would have like an infrastructure team or a network team that sets up the VPC and sets up these little guardrails. They place the subnets, they do the network ACLs, they connect all the inbound and outbound connectivity, VPC peering, transit gateways, all the stuff that's on the screen. And they would share something like a subnet to participants, right? This is a different account, perhaps. And these accounts, we call them participants, and they would launch their higher level services, maybe EC2 instances or databases or elastic load balancers, inside those subnets that you controlled for them. So I always used to think of it like your data scientists in your organization probably don't want to deal with internet gateways and route tables and subnet masks, and you probably don't want them to do it either. So here's kind of an example. We'll run through it. So you have your infrastructure team. They set up the foundation. They put some guardrails in the form of CIDRs, route tables, subnets, network ACLs, the connectivity in and out, internet gateways, VPC peering, transit gateway, so on and so forth. And your purple team comes and says, hey, I've got this new EKS workload. I'm really interested in getting it up and running. Can you help me out? So you say, sure, and you create a bunch of subnets. You assign a CIDR, you share a couple subnets with that account. Then they can go and launch their worker nodes and their clusters in those shared subnets, just as if it was their account, their VPC. Now, of course, that was pretty simple. So they went around the office. They were bragging. They were like, hey, it was really simple. I didn't need to learn that complicated calculus to do the subnet mask. And now the blue team is knocking on the door and saying, hey, I want something like that too. And so you launch up a new CIDR, you allocate these subnets, and you share those subnets as well. Now, I will mention that you can share a single subnet with multiple accounts. In this example, I'm not showing that, because what I'm showing here is that I wanted segmentation. I wanted to treat this as a multi-tenanted environment, and I'm going to create complete isolation between the two with network ACLs. So obviously, this architecture has a lot of desired features, especially for those teams that desire that flat network connectivity. Like, these are the customers a lot of the time that have their own overlay approach, or they're doing service mesh type functionality, or they're just starting out, right? So this has a lot of stuff around there. Policy control and isolation that the individual AWS account provides can be implemented at the single VPC layer here. So if you're an old-time AWS customer, you may be familiar with EC2 Classic. A lot of customers still were like, can you bring back EC2 Classic? This kind of is bringing back EC2 Classic because it allows your higher-level constructs to just interact at the EC2 layer and have somebody else that may be more familiar or competent with the infrastructure handling the infrastructure portion of it. So it abstracts the infrastructure to a bare minimum. So with that being said, depending on your operational model, the good can also be the bad, right? Like limiting the application owners can be a bad thing if they want that kind of flexibility. Obviously, you could provide them the IAM permissions of that account. They could assume a role and do all that kind of stuff. But natively, this could add complexity. It could be a bad thing. Another thing, just how we talked about the limits before. They're at the account level, the VPC level, or the region level. Any VPC limits aren't going to change overall. Account limits, yes, but not the VPC limits. So just because you put more accounts into VPC is not going to change those limits. The other thing that you got to think is that, like, what all are you putting in the VPC? What is your blast radius defined as? This is now becoming an area of a blast radius. And then ideally, I want to point out again, like a lot of the time when customers are looking at these type of designs, flat architectures, single VPC, multi-account or not multi-account, right? Single account, multi-account, doesn't matter. It's generally customers that are looking to optimize cost specifically, and they have a lot of dependencies between workloads. So by doing a single VPC, you don't introduce any of the mediums like transit gateway, VPC peering, so on and so forth, PrivateLink.
Cool. So now let's go over some of the patterns for multiple VPC architectures. So customers start their journey with a single VPC, typically, but they eventually end up having more than a single VPC. So sometimes it is to create that isolation boundary between your dev, test, and prod workloads, and other times is for complete isolation of your individual microservices. Now, we talk with customers who have less than 10 VPCs, all the way up to customers having hundreds of thousands of VPCs. Now, there are many reasons why a multiple account and multiple VPC strategy is preferred. Specifically for larger organizations, that can be solely to control and push beyond that AWS account-based limits. These are things like ENIs per account, security groups per account, or IAM roles per account. And another reason is to isolate your business unit and workload category. For example, if you have a workload which has PCI or HIPAA compliance, you could do that, or to separate your dev, test, and prod environments. Now, as the saying goes, like if something cuts both ways, it has both good as well as the bad aspect. So some of the good with this model is isolation of your blast radius, as your workloads are crossing the VPC as well as the account boundaries. Now, this is super important because this gives you that distributed service limits, which is helpful for you to scale on AWS. You can also get granular cost allocation per business unit tied to an account, and also achieve fine-grained access control for your identity and access management systems. However, with this approach, complexity increases in terms of IP management. Like what sort of IP range or CIDR should I allocate for a bunch of my VPCs? How does my DNS strategy look like? How do I implement networking between tons of VPCs? You would also have to think from how do you handle access control between resources that are across different VPCs and accounts with respect to both IAM as well as networking. So now we are going to dive right into different VPC networking connectivity patterns. So simple example, let's say you've got these 4 VPCs, and assuming you wanted all of these 4 VPCs to communicate with each other, you can get started by using VPC peering to build a full mesh of connectivity between these VPCs. Now, VPC peering is super simple to set up and does not introduce any sort of bandwidth limitations. VPC peering can be configured between VPCs, between the same region, across regions, or it could also be between different accounts. But as you can see over here, just with 4 VPCs, you had to configure 6 peering connections and accept as well as configure routing for each of them. Here's a quick math formula to give you perspective of what it takes to build a full mesh connectivity for using VPC peering. In this example, customer had 100 VPCs. So you would need 4950 number of peering connections to be configured and managed. So the number of peering connections almost exponentially increases with the number of VPCs in this design pattern. Some other limits to keep in mind is per VPC, you can only have 125 VPC peering connections, and you can have up to 1,000 routes in your route table of VPC. So let me introduce transit gateway into this mix. It's as simple as attaching all 4 VPCs to the transit gateway, and now they can all talk to each other. Furthermore, you decide that, you know what, I'm going to spin up few more VPCs. I want that full mesh connectivity. It's as simple as a single attachment API call, and they all join this fully routed environment. From an edge connectivity perspective, you can either have a single VPN attachment or a direct connect gateway attachment to establish that on-premises connectivity to the transit gateway, and the transit gateway then fans out to thousands of VPCs. So from a limit perspective, transit gateway is a service supported for much higher magnitudes of scale. So out of the box, you can get 10,000 routes inside a transit gateway route table, and you can have 5,000 attachments. So drilling down a little more into what is transit gateway, it can be broadly classified into 3 main properties. Number 1 is transit gateway is a regional service where you can aggregate your connectivity from on-premises by using either VPN connection or a direct connect connection. Think of it as like you're trying to consolidate your edge connectivity to AWS. Secondly, it scales up to 5,000 VPCs by default. And now we support equal cost multipath VPN. So you're still limited to that 1.25 gigs of throughput, but now you can horizontally scale using ECMP. And in-house, we have tested up to 50 gigs of throughput. Does not really mean that we cannot go higher. If you have a use case, please come and talk to us. And third is it gives you flexibility of routing, because what we are doing is when you create or when you make an API call of attach my VPC to this transit gateway, we are dropping an elastic network interface in that VPC subnet, and that ENI has to obey the route table rule of that VPC. Secondly, transit gateway also offers you multiple route tables, what we are going to refer for this talk as routing domains. And that gives you much more flexibility, which we are just going to show you in few slides. Clicker doesn't help?
No. Wrong routing.
There you go. Thanks. All right. So how to think about routing domains? So you should group your VPCs with same connectivity requirements or patterns or policies inside the same routing domain. However, associating these VPCs to the same routing domain does not automatically enable connectivity between them until you configure it. Now, inside the transit gateway routing domain, you can either have static routes or you can propagate the routes. We also give you an option of adding a black hole route, which means that it will drop the traffic if it matches the rule. And most important to keep in mind is if you would always need a return path in the routing domain if the destination VPC requires a different connectivity patterns. Now, this year, I remember, Justin, you were working with some of our customers specifically in designing inline firewalls or what we call the bump in the firewalls in a centralized fashions. Do you want to share your learnings there?
I think we got shared services.
Oh, I missed.
Cover that, and then I'll do bump in the wire.
Yeah, we can do that.
Let's do that.
Let me first cover this one. Yeah, use case one I think is very common is shared services VPC, where you put stuff like your monitoring, authentication, logging. And in this example, what we've done is you see 3 VPCs, each having their own application, and they belong to 3 different business units. Now, you want to ensure that the 3 VPCs do not talk to each other, but they talk to that shared services VPC. And they do have some dependencies on premises. That's why they need to talk using Direct Connect Gateway. Now, you can achieve this setup by using security group network ACLs, but now we want to ensure that we can use transit gateway routing domains to do the same thing. Now, in this model, we just created 2 routing domains, one for the VPCs, and the other one is for your shared services and direct connect gateway. So this is achieved by just using 2 routing domains, and historically, it's been a little difficult by using transit VPC and VPC peering. So Justin, I think now you can talk about the inline firewalls.
I'll talk about it. So, there's a couple different use cases for this, but a lot of the time, in the kind of more traditional, older style of security, a lot of people had this idea of perimeter security. Maybe it was a centralized firewall that everything was routed towards. Maybe it was some sort of bump of the wire, deep packet inspection. Maybe it was a NAT device. You name it, something that sits at the perimeter there. And so I'm going to call this, I'll probably call it 10 different things throughout this talk, but it's bump in the wire is what we're kind of thinking here. So if you visualize this architecture that's up on the screen here, on the left-hand side are kind of like your application VPCs. You could have thousands of these. In the middle is the transit gateway with 2 different routing domains, like Bhavin was talking about. And then on the right-hand side is that bump in the wire perimeter type thing that you want to send all the traffic through before it figures out what to do next. And so in this situation, I have a transit gateway, and I have attachments in the left-hand side, and I need to force the traffic into the transit gateway. So maybe that's a 0/0 routing statement in one of the routing tables. Maybe it's a more specific route. But one way or the other, you're sending the traffic into the transit gateway routing domain. So once the traffic is in the 0/0, the routing domain, it needs to know where to go next. And so in this situation, I want all traffic to go to the bump in the wire VPC. So I'm going to put a 0/0 static route saying all traffic go to the bump in the wire VPC. Okay? So now if you look there, I've got the TGW attachments, the ENIs, the purple things that are in that right-hand side VPC. I've got them sitting in a different subnet than my instances that are the bump in the wire thing. Okay? I do that because I want the ability to put them in their own route table so that I can have a default route, a 0/0 route. When the traffic comes out of the transit gateway, I want to have a 0/0 route that says, all traffic that comes out of this interface, send it to the bump in the wire instance, the ENI. Okay? Like that. Okay? And so now I'm forcing the traffic into the bump of the wire instance. The reason why it has to be a different subnet is because now that it goes through the instance, the ENI of the instance needs to have another 0/0 route. Maybe it's going to the internet gateway. Maybe it's going back to the transit gateway. It could be multiple things, but it has to have a different 0/0 route in order to dictate the traffic. Usually in these situations, you probably have to do a source NAT on that instance. So if it's a firewall or anything like that, you're going to have to apply source NAT. Now, this is because you can fall into kind of an asymmetrical routing type issue. Okay? So this is typically what you need to do if that bump in the wire requires state, like a stateful firewall. It needs to come back and see both sides of it. So for situations where you maybe can't do NAT, that is a customer asks sometimes, there is a way to do it, but it has a lot of drawbacks. So I'm going to point it out here, but I'm going to caveat with maybe you should think about this. You can direct all the traffic to a single instance ENI. Okay? But if that instance ENI fails, you're going to have some logic that does the health check to find out that it fails in the first place and redirect the traffic to another instance. Okay, so something that a lot of customers ended up doing to kind of help with some of the remediation and automation of the failover, like the detection and remediation of that failure, is they're actually using ECMP and VPN on the transit gateway instead of using the attachment approach for this model. What this buys you is it allows you to set up the VPN tunnels that also have BGP. BGP would detect the failure, and it would automate the recovery. Okay? So in all these models, there are ways to do the no-NAT kind of non-asymmetrical routing type thing. They're really tough, though. Okay? So you really want to really dive into it and see if they're really needed. So like I was kind of alluding to, these are the conversations we get into with customers all the time. This is a 300-level talk, and this needs to be a 500-level discussion, right? Because there's a lot involved here. You got to weigh the pros and cons. And so I would really recommend, like, don't be scared to hit us up. Don't be scared to hit up your closest solutions architect or a qualified partner. You know, like, the thing that I always come across when we're dealing with these situations is, like, typically these can be solved in a more scalable, distributed way that also doesn't add significant cost, okay? So, like, let's take a look at that. Sometimes it's not possible, sometimes it is. The other thing is, like, are there native constructs that solve this already, and can we look at them? Is it an orchestration or control plane issue, or is it not, right? Like, can we things like security groups, network ACLs, black holing traffic in a transit gateway, Amazon guard duty, any of those things, can they help out? If you go down the approach of centralization, you're going to deal with things like packets per second limits, latency, the throughput, and dealing with the high availability constraints.
So we just covered the inter-VPC communication with the transit gateway, but how does your edge connectivity work with Direct Connect specifically? So for customers who have got multi-region architectures and are looking to use transit gateway in conjunction with Direct Connect gateway, there are a few best practices I'd like to share with you guys in order to make sure that the traffic follows your desired path. Now here you can see there are 2 on-premises locations in 2 different geographies. You need to use Direct Connect gateway so you can attach it to both transit gateways in 2 different regions. Now, for redundancy purposes, you may have both of your on-premises location advertising the same prefixes, and in order to achieve traffic predictability during the steady state and during failure state, you need to use local preference communities when you advertise your routes to AWS. So for example, the west location is preferred primary path for the prefix 10.100/16 and as a backup path for 10.200/16. We could achieve this by applying higher local preference community of 7224, 7300 to that route. And what that does is that it dictates the preferred egress path from AWS to use 10.100/16 for the west location. Now, over here you see a single Direct Connect gateway, and one DX gateway or a DX gateway itself is a redundant and a logical construct. So for this architecture, there is no hard requirement for you to use 2 separate Direct Connect gateways. So something important to consider is use different autonomous system numbers per region for your transit gateways. Think about the ASN strategy that you implement for your customer gateway device, transit gateway device, and the Direct Connect gateways. For dictating your traffic or kind of predicting the traffic, always use AWS local preference communities. And in this setup, test out or figure out how does your Direct Connect device redundancy look, location redundancy look, and most importantly, how is your application redundancy look like. Now, also test the failovers, like what does that look like? And in case if it fails over, how does it impact your application? In most cases, like how does it impact the application if you have got an elevated latency? Does it time out? How does it operate?
Now, almost all of our application communication operates with each other and communicates with each other via standard TCP 3-way handshakes. Some of it doesn't, right? If you've got some sort of client-side load balancer where maybe you've got a broker that tells the client, hey, go talk to this specific backend instead of a load balancer, like that's not a PrivateLink use case. But for typical TCP client-server relationships where you got a client on one side and a server that lives in a different VPC, PrivateLink was purpose-built for this reason, okay? So you're basically poking a hole into another VPC to provide a service that's on a specific port and a specific IP address to another VPC. Now, this is different than if you were to do VPC peering or transit gateway because it's only poking a hole in for that service. It's not providing bidirectional connectivity for the whole VPCs. Okay, so like, why are people using this? Okay, so first off, it is simple. It completely limits exposure. So I think of PrivateLink almost as a security feature, not just network plumbing. Something that a lot of people aren't taking advantage of, I think, actually, is that it supports IAM policy on the endpoint itself. And the biggest thing that most customers use this for, that we talked about in the evolution, was it completely solves large, complex network address translation. And this is specifically important when you realize that like every single VPC you allocated was the same 10/16. Super common. The other thing I noticed is that it actually works across all AWS mediums. So whether that's Direct Connect, VPC peering, so on and so forth. Now, like we were talking about, if your application is not performing that traditional client-server handshake, the client-server relationship, TCP handshake, PrivateLink might not be the right fit. And if you have, depending on your traffic profile, there may be more efficient ways of deploying PrivateLink that we'll cover in just a second here. This is one of them. So some customers have opted for hosting PrivateLink endpoints in a shared services VPC. Now, they do this sometimes to avoid the cost of the endpoint itself. Okay? Now, that works for some use cases. But you have to think, depending on your traffic profile, if you're trying to avoid the endpoint cost, but you have a Kinesis endpoint or some sort of thing that's using a lot of bandwidth, you might end up paying more with the data transfer cost, pushing it over something like Transit Gateway or VPC peering, than you would by just hosting the endpoint itself. So that is one thing to consider. The other thing to consider in this situation is when you create a private link, we create a private hosted zone on your behalf, the service does, and we give a URI to it, right? A domain, fully qualified domain name for these endpoints. You don't own that private hosted zone. The service, the private link service does. So you can't associate it to the other VPCs. If you want to do that, you have to create a new private hosted zone, do a CNAME to the endpoints, and then associate that private hosted zone. There's a lot going on there. There's a white paper we're going to show you in just a second here that will definitely take a picture if you're interested in this model. It will go into this in depth. Okay, so on that shared services VPC, these are the things to consider here, right? These are the things. If you're looking to reduce costs on private link endpoints, this may be an option for you. Not always, depending on the traffic profile. Data processing fees may be more than the other. The other thing I would say is the private hosted zone association. We'll show you the link in there in just a second.
Cool. So now let's cover some of the hybrid connectivity model and the options that you have with AWS today. So let's start off with AWS site-to-site VPN connectivity. So the first option is to terminate your site-to-site VPN connection on a transit gateway, which is a regional service, and then transit gateway fans out connectivity to thousands of VPCs. The second model is to terminate your site-to-site VPN connection on a VGW, which is called Virtual Private Gateway, and that is attached to an individual VPC. And in the third option, you terminate your VPN on an EC2 instance, which is running VPN software, either from AWS Marketplace, or it could also be running something like OpenSwan, StrongSwan. Now, I won't be touching all of the numbers over here, but I've copied them for your reference because it's something important to keep in mind. Almost all of the customers should be looking at using Transit Gateway for their VPN termination. It simplifies the administration by reducing the number of VPN tunnels and BGP sessions to manage, and it scales horizontally in terms of throughput as well as scale of number of VPCs. So while VPN is a great option to get started, it's over the internet and might not be suitable for certain production traffic. Hence, many customers choose AWS Direct Connect, which provides high bandwidth, dedicated fiber connectivity between customer data center and AWS. Now, you can configure multiple private virtual interfaces on a physical Direct Connect and terminate them on VGW, which gets attached to individual VPCs. In the second approach, you can terminate your private VIF on a Direct Connect gateway, and that Direct Connect gateway can be attached to 10 VPCs, which could be spanning across multiple regions. And in the third approach, you can configure a transit virtual interface, terminate your BGP session on a Direct Connect gateway, and this Direct Connect gateway can be attached to 3 transit gateways across multiple regions. So quickly from a limit perspective, and this is more around how many BGP sessions you would need to reach a VPC. So in the first model, for reaching a VPC, you need 1 BGP session, so 1-to-1 ratio. In the second model, you create 1 BGP session to Direct Connect gateway, and you get access to 10 VPCs. And in the third model, 1 BGP session to Direct Connect gateway, and since Transit Gateway is a scalable product which can fan to thousands of VPCs, you potentially have an option to just configure 1 BGP session and get access to thousands of VPCs across 3 regions. Now, from a AWS prefix perspective, like how many routes can you advertise and how many can your router receive? In the first model, you can advertise 100 routes to AWS, and you will get individual VPC CIDR on your private virtual interface. For the second model, you are still limited to 100 routes, and from AWS side, you will get up to 10 VPC CIDRs. And in the third model, you are still limited to 100 routes to be advertised, but each transit gateway can advertise 20 prefixes to the Direct Connect gateway. And since you can attach 3 of those to a Direct Connect gateway, in total, you can get 60 routes back to your on-premises. So this was more of hybrid networking. But with that, you would also have to consider some things about hybrid DNS. How does that look like?
Perfect. So here's kind of the situation. You've got connectivity between your on-premise data center and your stuff in AWS. You got private zones on-prem. You got private zones in the cloud. So this is super common for hybrid scenarios. And last year, we launched an additional service as part of Route 53 called Route 53 Resolver. So what this does is it gives you 3 things. Okay? The first is an inbound endpoint. And this endpoint is basically the target for your servers on-prem, your resolvers on-prem, to use conditional forwarding rules to point AWS resources toward those inbound endpoints. Okay? That's the first thing. The second thing is outbound endpoints. This is the opposite. It's outbound interfaces, ENIs, that have reachability to over Direct Connect or VPN or whatever the case may be, to your on-premise resolvers, where we redirect queries to go and resolve to. And the third is resolver rules. These are basically the conditional forwarding rules for your AWS VPCs. You create these conditional forwarding rules that say, for these domains, resolve them on-prem through those outbound endpoints. And for these rules, local maybe, all Amazon stuff, resolve those local. So it allows you that flexibility. So here's the kind of main takeaways here. And I'll cover just the top 2 here because the other ones are just limit type stuff. This is the way you want to forward queries between alternate DNS servers. We built this for this reason, and it is the most scalable option that you have. I do want to call it too that this is not a substitute for associating private hosted zones between VPCs, right? So if you're trying to get zones between VPCs, that's private hosted zone association. Okay, so those are the 2 that we get a lot of questions on. So here's the DNS white paper that I was talking about. If you were interested in the shared services VPC concept, or you want to dive a little bit deeper into VPC, I updated this white paper with several of my colleagues just in September. And so it should be up to date. So I definitely recommend checking that out. Now, another super common one. How do I access dependencies on-premise that have overlapping IP space? 10/16, 10/16, or something like that. It's like nobody uses 192 addresses anymore, 192.168. OK, so you got, this is the PrivateLink model that we covered at the very beginning. So in this model, you have services that live on-prem, and you have services that live in the cloud. And you want to basically share those resources. So ideally, you would have IPv6, and that would solve it, but that's not always an option. So one option is this concept of like a mediator VPC or a NAT VPC. And with this model, you're basically setting up back-to-back bidirectional private links. And they're exposing endpoints on-prem and in the cloud. Ideally, those are some sort of virtual interface. You're not targeting like a single server or something like that. Maybe it's a load balancer on-premise. So here's a closer look. Your client in the VPC has the IP of 10.1.0.8 up on top. And the server on-prem has the same IP address. And so here, you basically put the private link in the client's VPC. You have a network load balancer sitting in the mediator or NAT VPC. And it has an IP target that's going across Direct Connect over to the on-prem. Now, when the server gets the request will come from that mediator IP address range. This is essentially the reverse direction. Now I've got a private link sitting in the mediator VPC, the NAT VPC, and I'm exposing my service via private link and a network load balancer in the VPC itself. Client, server, same IP addresses, solves the NAT issue there. So very helpful.
So now we have gone through several VPC and hybrid networking architectures, and we have also covered some of the critical considerations that you need to think through while you are constantly designing or evolving your architecture. The 4 tenets of success that we have put across each and every architecture is super helpful. But how can you help being a solutions architect for your own organization? What does that even mean? So what is an SA exactly? Someone who solves business problems with technical solutions by working with customers, operations teams, developers, and other stakeholders for a product or a service. They do this by asking a lot of questions and getting their hands dirty by doing proof of concept and helping scale the workloads by sharing best practices with various stakeholders in the organization. So now that I've gone through what an SA is and what an SA does exactly, it's important to figure out right set of questions before deciding on the first stage of your architectural evolution. How do I identify the right architecture? What sort of questions should I be asking?
So there's a few questions that, like, literally you should be asking about every single workload that you're onboarding and the teams you're working with. And the first one that always comes up is, like, what is the scaling factor? What am I dealing with here? Like, is it throughput? Is it latency? Is it I/O bound, TPS, transactions per second? Like, what are we dealing with here? What kind of workload is it? The next one that I think a lot of people actually don't spend enough time on, and I think you should, is what is the dependency matrix? What dependencies do I have? What do I need to communicate with? And what needs to communicate to me? Like, if I go down, who's having a bad day? The other is understanding the source and the destination and what type of traffic profile it is. So like we were talking about with PrivateLink, understand if this is like a 3-way handshake, TCP client-server relationship, or is it some sort of server-to-server, or is it multicast, or like what is it? And also, what's the source and the destination? Is this thing in the same subnet as me? Is it in the same VPC as me? Or is my client on some cell tower in a very rural area that has 50% packet loss? You're going to treat these differently. And one that you should tackle right off the bat is, are there any compliance or regulatory constraints? This can greatly help shape your architecture decisions. AWS's implementation of ubiquitous encryption covers the entire stack, providing underlying encryption in transit and at rest. We also provide the tools necessary for you to encrypt your higher level constructs. So keep in mind that network encryption is never a substitute for application layer encryption, authentication, and authorization. You know, understand what is the application SLA. Like, what are your application teams? What is their SLA? And how do they handle degradation? And my favorite is, it better to fail some of them, or is it better to kind of degrade every single one of them? Focus on identifying the SLA with your partners. A lot of the time, architectures are over-designed, which just adds complexity. I'm not trying to talk you out of adding redundancy, but I am trying to get you to ask the right questions to make sure you're designing something that's operational. 3 nines means 43 minutes a month for recovery time. 5 nines is 26 seconds a month. That means if you have 2 issues a year, you have 2.5 minutes to resolve the issue. And in 2.5 minutes, you can't get a human involved. Your system has to be 100% automated. The question you need to ask is if you really need 5 nines. Because if you do, and your system can't handle that automation, then you need to revisit with your stakeholders and understand what their business SLAs are. And so after working with your stakeholders and asking the questions we just went over, you should have a deep understanding of what their business objectives are and their technical requirements. So what do you do next?
So next is, the most important thing is to define your priorities. Now, if you all remember the 5 pillars of well-architected framework, almost 2 pillars are non-negotiable. The first is operational excellence. Now, if you cannot manage the system, it doesn't really matter how fast and reliable it is. And the second is security. So if for no other reason data breaches are expensive, And depending on your workload, they can have serious effects on human as well as financial circumstances. So that leaves us to reliability, performance, and cost optimization. So the old saying back in the day was that you could either have it fast, reliable, or cheap. Pick two. With AWS, we have built mechanism that helps you to scale your systems up and down in a cost-effective manner, but still there are trade-offs that needs to be considered. You need to work closely with each and every stakeholders of yours and help them define these priorities and get alignment. Transparency and communication is the key here.
The second is to embrace this concept of tiny bubbles. So companies start off as one thing, and they end up as a completely different thing. So whether through acquisition or through organic growth, you need to be prepared to adapt to the constantly evolving architecture. Over the last 12 months, Bhavin and I have worked with AWS's largest scaled customers, and the theme has been around, what does my next generation architecture look like? Now, a lot of these customers, not all of them, have been around and in the cloud since day one and went through the migration from EC2 Classic to VPC, which at that time was the next generation. Today, for reasons such as policy isolation, blast radius reduction, agility, more granular observability, and to better deal with account-based limits, every single one of those customers is implementing a multi-account, multi-VPC style architecture. So focus on developing automation and expertise in managing distributed VPCs instead of spending all your time trying to figure out the perfect VPC. So we put airbags in cars and separation between freeway directions. And these are kind of like mechanisms or guardrails because we can't chauffeur everyone around town. The network needs to get out of the way. Your goal as an architect is to remove the friction so that you can allow your teams to deploy in a safe and efficient fashion.
And last but not the least is keep it simple. So not everyone here today has the same scale or need that these customers have, which also needs to be considered. For many of you, the philosophy of less is more will win out. You must be able to operationalize and secure your infrastructure. Now, at the beginning of our presentation, I walked you through a real example of customers starting small and growing large. If you start investing in automating your infrastructure and integrating the tooling that is available with AWS to provide more observability needed to operate your infrastructure, you can grow organically and learn what works for your organization as you go in this journey. This is what the question matrix was all about. There is no one size that fits all. Your organization is unique, and the best architecture or the right architecture is the one which you can manage that provides your customers with the best experience possible.
Dun, dun, dun.
And now we have the most important slide to show. It's about, you came to reInvent to learn, but it doesn't stop here. So keep reinventing with the resources from AWS training and certification for networking for you and your team. And visit these links above for more details. Now, before I move to the next slide of thanking you guys for your time, there are few stickers that we have for networking fans over here. They can grab it from here. And thank you for your time. And please do fill up the feedback in your mobile. Thanks a lot.
We'll be up here for as long.